Hey kids, Miss Kulkarni here. Let's continue with some more calculations on weak acids and bases. So let's begin. First of all, weak acids and bases are the one which do not ionize till 100%. And actually, they form equilibrium between reactants and products much earlier than that. Also keep in mind, larger the value of Ka or Kb, that means there will be more product formed and then we will have higher ionization, and that means acid or base will be stronger. So how do we define percent ionization? It is the concentration of hydrogen ion to the concentration of acid times 100, or if it's a base, we only change it to hydroxide to the base concentration, and that times 100. Now what are the simple steps in solving the problems? The very first thing is you need to write down a dissociation equation or a reaction for an acid or of course for base. Second thing is, keep in mind, we are going to substitute for K equilibrium, Ka or Kb, the constant for acid or base. And then we set a table which we call as Rice table. What does Rice stand for? R stands for reaction. I stands for initial concentration. C is change in concentration, and E is ending or equilibrium concentration. So here is our first problem. We have been given acetic acid, and that's the formula for acetic acid. The molarity is 2.5 molar, and we have to find out pH and percent ionization. So let's begin. If the molarity is given to you as 2.5, that is the initial concentration for that acid. And at time t equal to 0, we have no ionization. That means each of the ion will be equal to 0. Now remember, weak acid or base is going to ionize partially. So let's say if X is the amount which is ionizing, how much we are going to get for each ion? If you look at the mole ratio, the ratio is 1:1:1. That means if we have X moles dissociating, we are going to find out X moles of each of the ion. So how much will be remaining, ending or final concentration at equilibrium? This will be 2.5 minus X. This will be X and this will be X. Now again, X is extremely small amount. So 2.5 minus X can be roughly about equal to 2.5. We can completely ignore that small quantity X. Okay, now in order to find out pH, we need to find out value for X. So let's go back to our equation K equilibrium. This is products divided by reactants, and we have these two ions as products. So let's write down those two. And our reactant is the beginning acid, which is acetic acid. So if you actually plug in the values for K equilibrium, what do we get? We get this equation. That's the value of Ka for acid. X and X are the concentrations for each of the ion respectively, and 2.5 is the concentration for the acid. So this is simply X squared divided by 2.5, and when we solve for X, what do we get? We get the answer 0.0067. Now remember, X is same as hydrogen ion. So in a way, indirectly we are getting hydrogen ion concentration. Once when we have that, can we find out pH? Of course we can, because pH is equal to negative log of hydrogen ion concentration. That means it is negative log of 0.0067. 0067, which is nothing but, now how do we find out percent ionization for acid? That is hydrogen ion concentration divided by the acid concentration at equilibrium, and that times 100. So let's plug the values for each of those. This is 0.0067 and the acid concentration is 2.5, and that times 100. And what's the answer? The answer is 0.268%. Alright, our task is to find out which of the two acids is relatively stronger acid. They both are weak, but which is relatively stronger? How do we find out? We look at Ka for each of the acid, and those are respectively values for acetic acid and hypochlorous acid. Obviously, this value is higher value. Higher the value of Ka, that means the concentration of product is also higher. That means percent ionization also goes up. So that makes acetic acid as the winning candidate. That is relatively stronger acid than hypochlorous acid. Alright, let's do some calculations with weak bases now. This is ammonia, and ammonia is NH3. When we write the ammonia hydrolysis, keep in mind we have to add H2O as one of the reactant, and it's going to give rise to hydroxide ions there. So just like we did for acid, the molarity is known as 0.25. So we begin with initial concentration as 0.25, and at time t equal to 0 we have no more ions, that's equal to 0. And when X moles are ionizing, what do we get the relative ratio for ions? It's 1 to 1 to 1. So we are going to get X ions of ammonium and X ions for hydroxide. So what is the ending concentration at equilibrium? This will be 0.25 minus X, and remember again, X is going to be too small, so that will be equal to 0.25, and this will be X, and hydroxide will also be X. What is the value for Kb? It is products divided by reactants, and products are ammonium ion times it is hydroxide ion, and the reactants are nothing but only ammonia. Water is liquid, so we won't consider that. Okay, now we are going to put the value for Kb and also the values which we obtain at equilibrium concentration there. So Kb for ammonia is 1.8 times 10 to negative fifth, and each of this is equal to X. Ammonium and hydroxide both are equal to X, and the concentration for ammonium is 0.25. So when we solve this, X is equal to 2.12 10 to negative 3 molar. Now what actually is X? X is equal to hydroxide concentration. So we can find out POH, and POH will be negative log of the hydroxide concentration. That comes out to be 2.67, and if that is the value for POH, pH will be 14 minus 2.67, and that gives you 11.33 as a value for pH. Alright, let's move on to find the percent ionization, and that is going to be hydroxide divided by ammonia times 100. So what exactly is that value? That will be X divided by 0.25. That times 100. And when you plug the value for x as 2.12, 10 to negative 3, and when we solve that, okay, which gives you final answer as 0.848. Let's do one more problem with this weak base, and let's complete the table first. Alright, so this is what we get when we complete the table. And then this is roughly equal to 0.55. And when we use the KB value, we end up having this equation. And then that gives you value for x as 6.9964 times 10 to the negative 4. If x is equal to hydroxide concentration, we can find out POH, that's negative log of 6.9964 10 to negative 4, and that is equal to 3.16. So with that we can find out pH will be 14 minus 3.16, which will be 10.84. Coming to percent ionization, when we plug the values, this is what we get. Hydroxide is X, N2H4 is 0.55, and then times 100, and value of X is something which we figured out over here. And when we plug those values and solve, the final answer comes out to be 0.13%. Now let's work on some reverse calculation. It's simple, just we work backwards. So over here, we know that there is an acid for which the pH is 5.255, and we have to find out what is the molarity for the acid, and of course we find out percent I for that. So that's the equation for the acid. If the molarity is not known, let's imagine that that is M, and we are going to complete the table as we were doing exactly same way. So if we have X moles dissociating, we get X moles of ions. This will be M minus X, this will be X, and then that's roughly equal to M. This is what we get for the formula for Ka. When we plug the value, this is what we get. Now X is hydrogen ion concentration. So how do you find out using pH? pH is 5.255. So obviously hydrogen ion will be 10 to negative 5.255, and that gives you answer as 5.556 times 10 to negative 6. When we plug the value of X in this equation, this is what we get. And when we solve that, the molarity for that is 0.0630. How do you find a percent ionization? That's going to be X divided by M times 100. And when we plug the values of X and M both, this is what we get. And when we solve that, the final answer is 0.0088. In this final problem, there is a base given morphine, and I'm going to use that as simply B, and that's the reaction we get for base hydrolysis. Let's complete the table using M as the molarity and X is the amount dissociated. So this is what we obtain when we complete the table. Now let's plug the values of Kb and solve for molarity. Okay, this is what we get. What is X? We can find X using pH value. So pH is 9.25. With that, we can find POH. POH will be 14 minus 9.25, which is 4.75. And if you know POH, you can find out hydroxide concentration. That will be 10 to negative 4.75, and that gives you the value as 1.778 times 10 to negative 5th. So let's go ahead and plug that value over here. So what's the value of m we are getting finally? 2.0 10 to negative 4 as a molarity for the base. Now the last part is to find the percent ionization, and that is plugging the values for both X and M. So percent ionization is going to be 1.778 times 10 to negative 5th divided by the molarity which we found, 2.0 10 to negative 4, and all of that times 100. And when we solve, we get percent I equals to 8.89%. So I hope you guys enjoyed the video. I will see you again in next video. Until then, bye.